for the voltage of the resistor, pi over 6.
And that's just given?
Yeah, that was given. Oh, there. Let's not forget. The other rule.
Now, is Eli made of ice, or does he work for immigration?
I will let you interpret it however you wish.
When I read Iceman, I was thinking of like way back in the day when people used to go up like mountains to like pick ice off and then bring it down.
Oh. You can go that way too. It's a throwback.
Speaking of the contract killer from the 80s that killed like over like 100 people for like the mob, the Iceman.
We have very distinct interpretations.
He's icing people.
Or he's a diamond merchant.
Yeah.
Okay, so getting away from the literary aspects of it.
Or he's wearing ice, which is why he's the Iceman.
Yeah.
Dripping in ice.
All right, so I said, so given in the problem, let's make the voltage phasor for the resistor at pi over 6, which is basically 30 degrees. Not basically, it is 30 degrees. So I tried to sketch out the 30-degree angle, and so this is going to be voltage for the resistor. What else has the exact same phasor?
The current for the resistor?
That'll have the same phase, but we'll have the same phasor.
Is the voltage in the parallel circuit, is that the same?
Yes.
Okay, so VR equals VC?
And I just might label it as VRC at some point. Now I know that for resistance, the current is in phase with the voltage, so as Pat was hinting at, I would be in the exact same direction. So that is I for the resistor. And I really, whether I make it bigger or smaller, they're different units, different set of scales, but you know, pointing in the same direction.
So I noticed that there's kind of like a rule for everything in terms of direction or relating it to a different component for the 8 phasors, except for the power supply. Is there a rule for that?
Well, the current coming out of the power supply better be the sum of the current going across the resistor and going across the capacitor. Those Kirchhoff's junction rule still applies
Okay.
to the instantaneous values.
I meant like I get what you're saying. I meant like a shorthand trick, like I guess the Eli the Iceman thing, or the VR will always be in phase with IR. So it's different depending on the scenario for the power supply.
Oh, yeah,
phasors?
yeah, the
Okay.
current from out of the power supply would change
Okay.
as impedance changes as well. All right, so using the Iceman, in which direction would the current from the capacitor point? And recall, phasors are, they treat them like arrows that are spinning all counterclockwise. So that, basically, omega, and your frequency in that direction, and your speed of the arrows, whichever way you want to look at it.
Current is 90 degrees for the voltage of the capacitor.
Yep, it leads. So, see, current, I'm doing green. Try that again.
You can do it, Dr. Fox.
That's a right angle. And so that's the current for the capacitor. It's ahead of the voltage by 90 degrees. That's the ice, I before E. I know that whatever currents flowing across the inductor splits go across the capacitor and the resistor, so I sub L should be the sum of these two current phasors. So I sub L, which also is the same for the power supply. Because whatever comes out of the power supply has to go across the inductor. So at this point, I got 1, 2, 3, 4, 5, 6. I have 6 in my phasers. I have 2 more phasers to go. The 6 phasers, I got VR, VC. I have IR, IL, IPS, and IC.
At this point, can you find the angle of the current of the power supply or not yet?
Define the what?
The angle of the current of the power supply or not yet?
Let's do that. There is enough information here to define that, but between the two boards.
Yeah, okay.
But let's get the phasers down first before we start getting into those weeds.
Yeah.
What do we know about in which direction will the voltage of the inductor go?
Did it go 90 degrees ahead of its current?
Yeah. Eli voltage leads the current. That's 90 degrees. And so the last phaser to put on the diagram is the power supply. Well, I know, again, Kirchhoff's voltage rule, I have some voltage going across here, which then has to lose it all going across those, so this would be the sum of these two voltages. So I'm just gonna add these two. That's really close to that one. I am going to change some stuff there so that they don't overlap as badly. Let's make that one longer. So that's VL. It's supposed to look like a parallelogram.
I can see it.
I would assume in your notes, you'll name it. Now, I really don't know whether VL, and this isn't L here, despite my attempts to make it look like an L. I don't know if VL should be that long or shorter. I don't know how long VL is. It's going to affect where E sub 0 is. I just know that E sub 0 is somewhere between VR or VRC and VL. It's somewhere between. Yes?
When I was looking at, I was trying to apply Kirchhoff's rules to the master set, and I'm just gonna ask, like, obviously this is the correct way, I'm just gonna ask this question so I don't make this mistake in the future, but, I said that all of the voltages add up to 0. And then I put the power supply on the other side so that the negative power supply equals the sum of the two other voltage phasers. And so for the master set question, if it was the same as this scenario, I actually put it opposite, like that negative vector.
A different way of thinking about it is if I'm going from here to here, my voltage is the same either way. And so, yeah, the sum adds up to 0, or the way that these are generally done, or the way that these are done, is you're basically looking at going from this to this. In essence, that sum equals that. As opposed to this minus, this is the opposite of the sum of those.
Okay.
All right, other questions? All right, so we can get one of these really quickly, because the basic format is some magnitude, some phase shift. Well, I know what it is for the power supply right here. I know that VPS is equal to 300 volts. That's my epsilon sub 9. times the cosine of, well, omega. What is omega?
100 pi, I mean, whatever that is.
Yeah, okay, 100 pi. So 314.159 T, that's radians per second. Plus 0. Nope, oops. I don't know phi yet. Plus phi V, yes. So I got part of information right there. VR, I know the phase shift here, so this is some magnitude of VR times the cosine of 314.159 radians per second T plus pi over 6. And that's gonna be the same for this, they're both. So VR and VC are the same thing. All right, let's see if we can nail down some of these phase shifts here. I know this angle, so let's go for that one. I know that angle. I know that IC is 90 degrees past that, so I can find that angle. So let's go ahead and do that. Phi for the current, for the capacitor. What is it?
120.
Pardon?
120.
Or 2 pi over 3.
Wait, how did we go about getting 2 pi over 3?
Well, I know that the voltage for the capacitor is at pi over 6, and that the current for the capacitor is 90 degrees ahead of it.
Oh, okay.
So just add 90 degrees or pi over 2. All right, so I've got someplace to keep
Sorry.
track of this stuff.
Would you mind going over that one more time? I really struggled for everything that wasn't already defined, like for pi over 6. Or...
All right, I know that the phase shift of VR and VC is pi over 6. I gave it to you for VR, but for VC, because it's in parallel, the voltage phasors would be the same. I know that for the current for the capacitor, it's 90 degrees ahead of it. And so I just add 90 degrees to this angle.
Oh, okay.
Okay, I'm gonna reorganize this. So it doesn't take as much room. All right, so for current, I'm gonna have magnitude and I'm gonna have angle. So power supply, I of newt, R, L, C. I know this angle is pi over 6. For voltage, power supply, I'm gonna have some magnitude and I'm gonna have an angle. R, L, DC, and I know this is 300 volts. I know this is pi over 6, and this is pi over 6. And we have I sub C is 2 pi over 3. At some point, it'll be beneficial to actually have a value for that. But for now, don't need it. Questions up to here? All right, so we have, there it is. Because I have IC and IR, I can figure out this angle right here, which goes back to something Pat was asking about before. I'm gonna just label this angle here, theta 1. I know that the tangent of theta 1 is the opposite over the adjacent. This is a right angle because that's a 90-degree angle there. So this is the tangent of theta is equal to opposite of the adjacent, which is I sub c over I sub r. Well, I don't know what I c and I r are, but I do know that I is the voltage across C divided by the capacitive reactance, and this is the voltage across R divided by the resistance. The Ohm's law variations from over there. My voltages are the same, so this just becomes R over X sub C. Well, I know what R is, that's given. X sub C I could calculate because I now know omega and I know the capacitance. This is equal to 1 over 314.159 radians per second times coulombs, which is, coulombs was, no, wrong C, capacitance, 30 times 10 to the negative 6 farads. And what do we get for X sub C?
Got 106.10.
106.10. Let's take it out 2 more decimal places.
1033.
33?
Yep.
Got 3-4.
That's 3-4.
Units?
Radians per second farad.
And then take the reciprocal.
Oh,
Is it not just
so then it's
ohms? Farads?
seconds over radians farad.
Otherwise known as
Ohms?
ohm. It's an ohm. If you wrote down seconds per radian farad, I would accept that. So this becomes 150 divided by 106.1034. And so theta sub 1 is equal to
Do you want the angle in radians or?
ultimately, yes, radians. So
I got 0.955 radians.
give me 2 more decimal places.
95515.
All right. So therefore, the phase of this vector right here, this is IL and IPS, is that angle that we just got plus pi over 6. Therefore, what is this phase in decimal form? These two are the same.
1.4787.
And so this would be 1.4787.
And is that for the inductor current?
That's the inductor current and the power supply current, because they're the same.
Gotcha.
So I now have that. I can figure out what the phase of VL is. What is the phase of VL? Conceptually, if not the actual number.
It's 90 degrees plus, or pi over 2 plus the phase of the current.
Yeah, so it's 90 degrees ahead of it, so that number that we just got plus pi over 2. So we get VL. Something.
3.04955.
Alright. So we have all but one phase. And this is the tricky one. The last one, the one that's the hardest one. So questions up to here before we tackle the last phase.
Wait, how did we get the? What did we compute to get the calculation for current and inductance?
How do we get the wait,
current.
which one?
The current calculation that we just did.
That phase?
Yeah.
We got that because when I created this phaser right here, it was the sum of these two phasers.
Mm-hmm.
If I add them, I've got I sub r going this way, and I plus I sub L, I sub c, and that sum, that's I sub L. The sum of those two, that's a 90-degree angle. So what I labeled that as theta 1 and solve for theta 1. It's the opposite over the adjacent, the right triangle. And so we got this angle here to be 0.95515. The phase though is always relative to 0, so 0 is that way. And so that total angle is this part right here, the pi over 6 plus theta 1.
Oh, and that's how we got the 1.47.
Yes.
Okay.
Other questions? All right, so now let's tackle